In the months before the greatest amphibious invasion in history, Allied planners grappled with a problem that was simultaneously mundane and absolutely critical. The liberation of Europe would require not just men and weapons, but something far less glamorous and far more essential: fuel. Millions upon millions of gallons of aviation fuel, diesel, and motor spirit would need to flow continuously from Britain to the advancing armies in France, feeding the tanks, trucks, aircraft, and countless other machines that modern warfare demanded. Without fuel, the most powerful army in the world would grind to a halt within days, its tanks silent, its aircraft grounded, its trucks immobile, and its entire strategic purpose frustrated not by German guns, but by the simple absence of petroleum. The planners knew this. They knew that logistics, the unglamorous science of getting supplies to the right place at the right time, would determine whether Operation Overlord succeeded or failed as surely as the courage of the men who would storm the beaches. And they knew that conventional methods of supplying fuel, tanker ships crossing the English Channel, exposed to German submarines and aircraft, were inadequate for the volume required and dangerously vulnerable to interdiction. What was needed was something that had never been attempted on anything approaching this scale: a submarine pipeline running beneath the waters of the English Channel, connecting British fuel reserves directly to the advancing Allied armies in France. The project was given a name that combined ambition and understatement in equal measure: Operation PLUTO, which stood for Pipeline Under the Ocean. This is the story of one of the most extraordinary engineering feats of the Second World War, a secret construction project that helped fuel the liberation of Europe and whose legacy endures in the infrastructure of the modern world. The fuel requirements of Operation Overlord were staggering by any previous standard of military logistics. The invasion planners calculated that the Allied armies, once established in France and beginning their advance toward Germany, would require approximately 1 million gallons of fuel per day at the initial stages, with this requirement growing rapidly as more forces were landed and the front expanded. For context, a single armoured division operating in active combat consumed approximately 60,000 gallons of fuel daily. The planned invasion force ultimately comprised dozens of divisions, hundreds of thousands of vehicles, and thousands of aircraft, all consuming fuel at rates that dwarfed anything previously experienced in warfare. The logistics challenge of supplying this enormous appetite across the English Channel, in the face of German opposition, under conditions of constant military pressure, was one of the most complex problems Allied planners faced. Tanker ships were the obvious solution, and they would indeed be used. But tankers had profound vulnerabilities. German U-boats had spent 4 years demonstrating their ability to sink Allied shipping at catastrophic rates before the Battle of the Atlantic was finally turned in the Allies' favour. German aircraft operating from bases in France and the Low Countries could reach the Channel and threaten shipping. Even with adequate anti-submarine and anti-aircraft protection, tankers were slow, their capacity was finite, and the logistical chain from British oil terminals to French beaches involved multiple vulnerable links. Furthermore, the beaches and ports where tankers could offload were limited in capacity and could be targeted by German artillery and bombing. The fuel supply chain was a critical vulnerability in the entire invasion plan, and the planners knew that if it could be disrupted, the invasion might stall despite success on the beaches. The concept of a submarine pipeline across the Channel was not entirely without precedent. Small submarine cables for telegraph communications had existed for nearly a century, and submarine pipelines for other purposes had been constructed in various locations. But a fuel pipeline crossing the English Channel, 21 miles at its shortest point between Dover and Calais, and considerably longer on alternative routes, carrying petroleum products at high pressure and in volumes measured in millions of gallons, was an engineering challenge of a completely different order. No one had built anything like it before. There were no established techniques for manufacturing pipe that could withstand the combination of water pressure, temperature variation, and the mechanical stresses of laying across the Channel seabed. There were no vessels designed to lay pipe at this scale and depth. There were no proven methods for connecting such a pipeline to onshore distribution systems on both ends. The engineers who were tasked with solving these problems were working in genuinely uncharted territory. The project was initiated in the early stages of invasion planning, with the recognition that if a submarine pipeline was to be operational by D-Day, or shortly thereafter, development and construction would need to begin immediately. A team of engineers was assembled, drawing on expertise from the oil industry, the telecommunications industry, which had experience with submarine cables, and military engineering. Among the key figures was Geoffrey Lloyd, the Secretary for Petroleum, who championed the project at governmental level and helped secure the resources and priority it needed. The engineering team included representatives from oil companies, cable manufacturers, and specialist engineering firms, all working under conditions of strict secrecy, aware that the project's value depended entirely on the Germans not knowing it existed. The fundamental engineering challenge was creating a pipe that could be manufactured in long continuous lengths, coiled onto a large drum or vessel for transportation, uncoiled and laid across the channel seabed, and then connected to pumping stations and distribution systems on both ends. The pipe had to be flexible enough to be coiled and uncoiled without damage, strong enough to withstand the mechanical stresses of laying and the water pressure when operational, and impermeable enough to contain petroleum products under high pressure without leaking. Early experimental designs used lead pipe, similar in concept to the lead cables used in submarine telecommunications, but this material proved inadequate for the required pressure and flow rates. The team eventually developed two distinct pipeline designs, each with different characteristics and manufacturing methods. The first design was designated HAS, an acronym derived from Hartley, Anglo-Iranian, and Siemens, the three organizations primarily responsible for its development. The HAIS pipe was essentially an armored submarine cable adapted for petroleum. Its core was a seamless lead pipe approximately 3 inches in internal diameter, surrounded by layers of paper impregnation and protective taping, wrapped in steel armor wires and finished with an outer protective covering. This design drew directly on submarine cable manufacturing technology, using similar production methods and machinery. The HAIS pipe was flexible, could be coiled onto large drums, and had good resistance to the mechanical stresses of laying. Its main limitation was relatively limited flow capacity due to its small internal diameter. The second design was called Hamel, named after its inventors H.A. Hammack and B.J. Ellis. The Hamel pipe was a more conventional steel pipe design, using steel in a spiral wound construction that provided both strength and flexibility. The steel pipe had a larger internal diameter than HAIS, approximately 3 inches, and could handle much greater flow rates. It was manufactured in lengths of approximately half a mile, which were then welded together on specialized ships and coiled onto enormous cylindrical drums called conundrum floats. These drums, measuring approximately 33 feet in diameter and built from metal frameworks, were towed across the channel while the pipe was uncoiled from them and laid on the seabed. The Hamel design was more complex to manufacture and lay than Hayes, but offered superior hydraulic performance once operational. The manufacturing program for both types of pipe was an industrial undertaking of considerable scale, conducted in facilities across Britain under conditions of strict security. Cable manufacturers who had normally produced submarine telegraph cables now produced HAIS pipeline. Steelworks and specialized manufacturers produced Hamel components. Welding was conducted at designated sites, and the completed pipe was loaded onto the storage drums and laying vessels that would transport it to the channel. The workers involved were told enough about what they were producing to perform their tasks, but not the full strategic context, with compartmentalization of information keeping the project's true purpose secret from all but a small number of people who needed to know the complete picture. The shore facilities required for PLUTO were equally challenging to create. On the British side, pumping stations needed to be established with connections to existing fuel distribution networks, capable of pumping petroleum through the submarine pipelines at sufficient pressure to move it across the channel. These stations had to be disguised from German aerial reconnaissance, hidden among existing industrial buildings or made to look like other types of infrastructure. On the French side, the pipeline would need to connect to onshore distribution networks, capable of distributing fuel to the advancing armies. Planning these shore facilities had to be done while considering not just the engineering requirements, but the operational situation. Where would Allied forces be when the pipeline became operational, and how could fuel be distributed from the pipeline terminus to forward units? The invasion of Normandy on June 6, 1944, preceded PLUTO becoming operational. The pipeline was not ready for D-Day itself, and the initial fuel supplies for the invasion were carried by conventional means: tankers, coastal vessels, and the innovative DUKW amphibious vehicles that could carry supplies from ship to shore. The jerry cans, the simple 5-gallon fuel containers, became critical logistics tools in the early stages of the campaign, with thousands of them flowing across the beaches every day. But everyone involved in the logistics planning knew this was insufficient for a sustained campaign. The pipeline had to be completed and become operational as quickly as possible after the invasion. The first PLUTO pipeline, running from Shanklin on the Isle of Wight to Cherbourg on the Normandy coast, was laid in August 1944, 2 months after D-Day. The distance across this stretch of the channel was approximately 70 miles, and the laying operation was conducted by specialised vessels that paid out the pipe from their drums while moving at low speed across the water. The operation was vulnerable to German attack, as a surface vessel moving slowly in the channel with a long trail of pipe behind it was an obvious target. Air cover was provided, and naval escorts accompanied the laying vessels, but the operation was inherently risky. Technical problems were also encountered. Early attempts at laying Hamel pipe experienced breaks and other difficulties that required the operation to be repeated. But eventually, after considerable difficulty and perseverance, the first pipeline was successfully laid across the channel bed and connected to pumping stations on both ends. The moment when the pumps were started and fuel began flowing through the pipeline beneath the channel was a quiet triumph of engineering and determination. There were no public celebrations, no announcements in the press, no newsreel cameras recording the event. The project was still classified, and the men who had spent months designing, manufacturing and laying the pipeline watched the pressure gauges and flow meters in their pumping stations with a mixture of professional satisfaction and private pride. Fuel was flowing from Britain to France through a pipe on the seabed, something that had never been done before on this scale, something that many experts had doubted could be done at all, and it was working. The PLUTO system expanded significantly as the campaign progressed. Additional pipelines were laid as more territory was liberated and as the supply needs of the advancing armies grew. Eventually, a system of multiple pipelines connected Britain to France, with the network on the French side extending progressively further as Allied forces advanced. The pipeline system was connected to fuel dumps, distribution points, and eventually to forward supply installations that fed the armies pushing toward Germany. The scale of the infrastructure that was created underground and underwater, beneath the channel and beneath French soil, was remarkable. A covert petroleum distribution network that was essential to the entire Allied advance. The flow rates achieved by PLUTO, once the system was fully operational, were substantial, though not always as great as planners had hoped. At peak operation, the pipelines delivered approximately 1 million gallons of fuel per day, meeting the original planning target. However, this represented a fraction of the total fuel demand of the advancing Allied armies, with the remainder still being supplied by tanker ships and coastal vessels. The contribution of PLUTO was therefore significant, but not as dominant as some post-war accounts have suggested. The pipeline's real value lay not just in the volume of fuel it delivered, but in the reliability and continuity of supply it provided, reducing the dependence on vulnerable shipping and giving logistical planners confidence that a baseline supply was always flowing. The operational security around PLUTO was remarkably successful. Despite the enormous scale of the project, involving thousands of workers and extending for months, German intelligence apparently had no clear knowledge of the pipeline system. German submarines were not tasked to find and cut the pipelines, which they theoretically could have attempted. German aircraft did not bomb the pumping stations, which were hidden but not invisible. The elaborate deception operations surrounding the entire Normandy invasion, including Operation Bodyguard and its sub-operations, helped mask the true nature of PLUTO from German intelligence, and the compartmentalization of information within the project prevented any single leaked piece of information from revealing the whole. The success of this operational security was itself a remarkable achievement, given that secrets shared among thousands are extraordinarily difficult to keep. The technical challenges encountered during PLUTO operations were numerous, and often required improvised solutions. Pipelines occasionally developed leaks, which had to be located and repaired, either from surface vessels or by divers in the difficult and dangerous conditions of the channel. Pumping equipment required maintenance under wartime conditions with limited spare parts and specialist technicians. Pressure management in a long submarine pipeline carrying petroleum was technically demanding, requiring careful monitoring and adjustment to maintain safe and efficient operation. The onshore distribution networks, extending across liberated France and eventually Belgium and the Netherlands, required constant expansion and maintenance as the front moved further from the Channel coast. These operational challenges were met by the personnel of PLUTO with the same ingenuity and determination that had characterized the project's development. The people who made PLUTO work represent one of the most diverse and unusual groups of any wartime operation. They included petroleum engineers from the major oil companies, cable-laying specialists from the telecommunications industry, Royal Navy personnel who operated the laying vessels and provided protection, Royal engineers who constructed and maintained the onshore facilities, and civilian workers who manufactured the pipe, built the pumping stations, and performed the countless technical tasks required to keep the system operational. These people came from very different backgrounds and cultures, and coordinating their work required considerable organizational skill and patience. Yet the urgency and importance of the task created a common purpose that transcended professional and organizational boundaries, producing the kind of collaborative achievement that characterized the best of the Allied war effort. The secrecy surrounding PLUTO meant that the people who built and operated it received little public recognition during or immediately after the war. Unlike the crews of the Dam Buster raid or the commandos who conducted famous operations, the engineers and workers of PLUTO laboured in anonymity, their extraordinary achievement hidden behind classifications that persisted for years after the war ended. When the project was eventually made public, the men and women who had built this pipeline under the ocean found that the world had moved on and that the immediate post-war era was more interested in the dramatic visible achievements of the war than in the quiet technical triumph of an underwater fuel pipeline. This anonymity was, in a sense, the final expression of the operational security that had protected the project during its most critical phase. The engineering lessons learned from PLUTO proved enormously valuable in the post-war development of submarine pipeline technology. The techniques developed for manufacturing flexible pipe that could be coiled, transported, and laid in large continuous lengths became foundational for the offshore oil and gas industry that developed rapidly in the 1950s and 60s. The methods for laying pipe across the seabed, for connecting submarine pipelines to onshore infrastructure, and for maintaining and repairing pipelines in difficult underwater conditions were all refined and extended in subsequent commercial applications. The North Sea oil fields, discovered in the 1960s and developed into a major petroleum resource, were exploited using pipeline technologies that had direct lineage from PLUTO. In this sense, the wartime project made a contribution that extended far beyond its immediate military purpose, helping to shape the infrastructure of the modern petroleum industry. The Hamel pipe design, in particular, influenced the development of what became known as flexible pipe technology, a category of submarine pipeline that is now used extensively in offshore oil and gas production. Modern flexible pipes are far more sophisticated than their PLUTO ancestors, using multiple layers of different materials to achieve combinations of strength, flexibility, and impermeability that would have seemed almost miraculous to the engineers of 1944. But the fundamental concept of a pipe flexible enough to be coiled and laid from a ship, yet strong enough to carry petroleum under pressure in difficult underwater conditions, was proven by PLUTO, and the offshore industry built on that proof. The historical assessment of Operation PLUTO's military significance has evolved over the decades since the war. Early accounts, coloured by the natural tendency to celebrate technical achievement, sometimes overstated the pipeline's role in Allied logistics. More careful historical analysis has established that PLUTO delivered a meaningful but not dominant share of Allied fuel requirements in the Northwest European campaign, with conventional shipping remaining the primary supply method throughout. The pipeline's contribution was important and its reliability valuable, but it was one component of a complex logistics system rather than the decisive element some early accounts suggested. This more nuanced assessment does not diminish PLUTO's achievement. It simply places it in proper context within the broader logistical effort that sustained the Allied advance from Normandy to Germany. The strategic value of PLUTO extended beyond the fuel it delivered to the confidence it provided logistical planners. Knowing that a pipeline connection existed between Britain and France gave planners a reliable baseline supply that was independent of weather, submarine activity, and German surface interference. This allowed them to plan forward operations with greater confidence in fuel availability, reducing the margin they needed to hold in reserve against supply disruptions. In the inherently uncertain world of military logistics, this confidence had real value that cannot be easily quantified, but was genuinely important to the planning and execution of the campaign. The physical legacy of PLUTO is largely invisible today. The pipelines themselves lie on the seabed of the English Channel, abandoned in place after the war when they were no longer needed. Some sections have been found by researchers using modern underwater survey equipment, lying in the Channel mud where they were laid 8 decades ago. The pumping stations on the Isle of Wight and in Normandy have been demolished or converted to other uses. The specialised laying vessels were scrapped or converted to peacetime purposes. The enormous conundrum drums, those bizarre cylindrical structures that were towed across the Channel while paying out pipe, were broken up for scrap. Almost nothing tangible remains of an engineering achievement that was, in its time, one of the most remarkable technical feats ever attempted. Yet the invisible legacy of PLUTO endures in the technology it pioneered, in the organisational and engineering knowledge it created, and in the broader story of Allied logistics that it represents. The liberation of Europe required not just the courage of the soldiers who fought on the beaches and in the hedgerows, but the technical ingenuity and organisational capability of the thousands of people who ensured that those soldiers had the fuel, ammunition, food, and equipment they needed to keep fighting. PLUTO was part of that logistics story, an extraordinary part, a part that pushed the boundaries of what engineering and human determination could achieve under the pressure of wartime necessity. The story of Operation PLUTO is ultimately a story about solving an impossible problem through ingenuity, determination, and the willingness to attempt something that had never been done before. The engineers who designed the pipeline, the workers who manufactured the pipe, the sailors who laid it across the Channel, and the technicians who kept it operating, all contributed to an achievement that was essential to the Allied victory in Northwest Europe. They worked in secrecy, received little recognition, and used techniques that had to be invented as they went. They succeeded because they had to, because the alternative was a logistics failure that might have compromised the entire campaign for the liberation of Europe. In a war full of dramatic weapons, famous battles, and celebrated heroes, Operation PLUTO stands as a reminder that wars are won as much by engineers and logistics specialists as by soldiers and commanders. The pipeline beneath the ocean, invisible and unsung, carrying fuel to the machines that fought for freedom, represents the unglamorous but absolutely essential foundation upon which military victory ultimately depends. Without the fuel that PLUTO and its companion supply systems delivered, the armies of liberation would have been walking, and walking armies, however brave, do not liberate continents from armies with tanks, trucks, and aircraft. The pipeline under the ocean, quiet and hidden on the seabed, helped make the difference between a stalled invasion and a successful liberation, and that contribution, however invisible, deserves to be remembered alongside the more visible achievements of the war that freed Europe from tyranny